Section 7.7 is about indeterminate forms, which come up when we're trying to find limits, and then a technique for finding some limits called L'Hopital's rule. So you have to be able to apply L'Hopital's rule as needed. It only applies in certain circumstances. You'll have to verify that you're in one of those circumstances and remember when it applies and when it doesn't. So a refresher on indeterminate forms. An indeterminate means you cannot decide an answer at that stage. It means do more work. We've seen these throughout the class, but it's kind of nice to have them all in one spot. So indeterminate forms, where you cannot just look at it as is and decide an answer. That happens when you get 0 over 0, infinity over infinity, with any kind of plus or minus combination. 0 times infinity or 0 times negative infinity. We've talked about like 0 times 5 always equals 0. 0 times any constant number always equals 0. But similarly, 5 times infinity is still infinity. 10 times infinity is still infinity. Infinity times some constant number is always infinity. So when you pair those two together and you multiply them, 0 times infinity is indeterminate. Infinity to the 0 power, 0 to the 0 power, infinity minus infinity. So these are just examples of cases when you're working with limits where you're going to have to do something else. You're going to have to rearrange. Other forms where you can find an answer. These are not indeterminate. You can figure out what they actually equal. Infinity plus infinity is infinity. Infinity times infinity is infinity, and so on. It's got some worked out for you. We've seen these before, but it's just kind of nice, again, to have them in one spot. All right, back in chapter 1, when we encountered an indeterminate form, all we knew about, really, at that point, was algebraic manipulation. So we would factor and try to cancel. We would rationalize. We would rewrite what we were taking the limit of. Maybe we got common denominators. It just kind of depended. So if we take a look at some of those, one example would have been to factor. And so starting with this limit, you're able to factor out a 2 on top. Once you're done with that, it's a difference of squares. And then you can see that the x plus 1's cancel. Once the x plus 1's cancel, you're able to just substitute in. They're getting to the negative 4 by taking 2 times negative 1 minus 1. You're just plugging in. Because remember, our easiest technique or thing to start with is just to take the number and plug it in when we're trying to find a limit. But if I get 0 over 0 or infinity over infinity, that doesn't work. We also saw in chapter 1 that if I'm approaching infinity and I just have a rational function, we can think about horizontal asymptotes of the function. And so we compare the degree on top and bottom. We see in this case that degree on top is 2, degree on bottom is 2. If the degrees match, that's when we take a ratio of the leading coefficients. So this limit will equal 3/2. So that was a 0 over 0 case first, and then an infinity over infinity case. This is another 0 over 0 case. And if we try some algebra, it's just rewriting. Like if you take a look at this expression and notice it has a common denominator and put it back together going to the left, you get what you started with. But it doesn't really help me in that case because e to the infinity is still infinity. And then, oops, sorry. Let me rewrite that. E to the 0 is what you would have over 0. So that becomes 1 over 0. Well, 1 over 0 approaches infinity. And then for the second part, the 1 over 0, well, 1 over 0 approaches infinity. So I'm left with infinity minus infinity, and I can't do anything there. That's indeterminate. And I've kind of exhausted my options as far as algebra. I've looked at common denominators, putting it together, taking it apart. I can't really do anything there. So algebraic manipulation isn't going to work for everything. But in chapter 1, that's really all we knew about. Well, now you know about derivatives, and it turns out there's a connection between derivatives and limits if you're in certain cases. So if I have an indeterminate form, 0 over 0 or infinity over infinity, those are the only two we're going to talk about for L'Hopital's rule. But if that's your indeterminate form, then you can apply L'Hopital's rule. And L'Hopital's rule talks about if you want to take the limit of a fraction, but the limit of this fraction gives you 0 over 0 or infinity over infinity, then you can apply L'Hopital's rule, and it turns out that these two limits are equal. If I just want to differentiate the top and differentiate the bottom and try again, try to take the limit again, I'm allowed to do that. They're actually equivalent, as long as your limits and your derivatives are existing. That's interesting to think about. If I want to take the limit of a fraction, and it's in 0 over 0 or infinity over infinity form, it turns out that I can just differentiate the top of the fraction, differentiate the bottom of the fraction, and try to take that limit. I don't even need quotient rule. I'm not differentiating the whole fraction. I'm just differentiating the top and differentiating the bottom. L'Hopital's rule does apply to one-sided limits. And if after you try it once, you still get that same 0 over 0 or infinity over infinity, you can continue to repeat the process as many times as you need to. So let's see some examples. I have seen this on some Calc BC examples of free response questions, so you are going to have to make sure that you can write it out, that you understand when it applies. So in order to do that, we would say the limit as x goes to 0 of e to the 2x minus 1 over x. That was that example on the last page that we couldn't really do anything with. If I just substitute in, I get 1 minus 1 over 0. I get 0 over 0. So, I'm going to abbreviate for right now, by L'Hopital's rule, then the limit as x goes to 0 of e to the 2x minus 1 over x is going to equal the limit as x goes to 0, and I'm going to differentiate the top. Derivative of the top will be e to the 2x, and then chain rule on that power means I have an extra 2 in front, 2e to the 2x, over derivative on the bottom is 1. Again, I'm not taking the derivative of the whole fraction. I'm not doing quotient rule. I'm just differentiating the top, differentiating the bottom, and by L'Hopital's rule, it tells me that those two limits are the same. Well, now let's try to take that limit by plugging in. So if I plug in 0, I get 2, and e to the 0 is 1 over 1. My answer is 2. So I was able to find the limit by being able to take derivatives. Again, though, you have to actually establish for L'Hopital's rule to work that your limit was equal to either 0 over 0 or infinity over infinity. That's the only time it applies. So in the next example, now I'm letting x approach negative infinity, and I have x squared over e to the negative x. So limit as x goes to negative infinity of x squared over e to the negative x is equal to, well, I would get infinity on top because I'm squaring. And then on the bottom, e to the, well, I'd have a double negative. That would really end up being e to the positive infinity. This is infinity over infinity. So, by L'Hopital's rule, and I'm just going to abbreviate for right here, the limit as x goes to negative infinity of x squared over e to the negative x is equal to the limit as x goes to negative infinity. And I'm going to take the derivative on the top, so I get 2x, over derivative on the bottom, I get e to the negative x. Chain rule on the negative x means I have a negative 1 that's in front. Okay, now I'm going to try to plug in. And that equals negative infinity over negative e to the infinity. So infinity over infinity again. So by L'Hopital's rule, that's equal to the limit as x goes to negative infinity. And now I am differentiating the top part of that fraction, so I get 2. And the bottom part of that fraction, I get e to the negative x times another negative 1 in front. So that's positive. Now I should be able to find the answer, because if you notice, starting with the x squared polynomial, every time you take a derivative, so x squared gets bumped back to an x, and then now that gets bumped back to a constant, and at that point I'm going to be able to find the answer. So it might take me a couple times of doing L'Hopital's rule, but now if I want to plug in, I would get 2 on top, e to the positive infinity on the bottom. So 2 over something very, very large, 2 over infinity, that approaches 0. But again, before you want to use L'Hopital's rule, you have to establish that you have either infinity over infinity or 0 over 0. So if I wanted to use it twice, I established that one time, and then again I established that it equaled infinity over infinity. So by L'Hopital's rule, I was able to differentiate again. Okay. Next example, if I just try to plug in, I'm going to get this limit is equal to e to the minus infinity times square root of infinity. Well, e to the minus infinity, that's 1 over e to the infinity. Square root of infinity is still infinity. But now I'm left with 0 times infinity, because this part zeroes out. Well, that's an indeterminate form. I can't tell you what the answer is. I cannot determine what the answer is at this point. But I also can't use L'Hopital's rule at this point because it's not 0 over 0 or infinity over infinity. It's 0 times infinity. So I need to rewrite this problem in a way that I have a fraction. So I'm going to rewrite it as the limit as x goes to infinity. I'm going to say this is equal to limit as x goes to infinity of square root of x over e to the x. I'm going to rewrite it as a fraction to start with. And that's going to equal infinity over infinity. So by L'Hopital's rule, the limit as x goes to infinity of that fraction is going to equal the limit as x goes to infinity, and I'm going to differentiate the top, 1/2 x to the negative half, over, and I'm going to differentiate the bottom, and it stays e to the x. Okay, let's try to see if I can actually get an answer from here, because I don't necessarily need L'Hopital's rule over and over and over again, so let's just kind of clean this up. This is the limit as x goes to infinity of 1 over 2 square root of x, and then times e to the x. Everything power-wise and variable-wise is on the bottom. So if you let 1 be over something that's very, very large, 1 over infinity is very, very small. It approaches 0. 1 over infinity approaches 0. So I didn't need L'Hopital's rule several times. I was able to just do it once and then rearrange and evaluate my answer. But remember, before I was able to use that technique, I had to establish that the limit was in infinity over infinity form. I could not use L'Hopital's rule when it was in 0 times infinity form. Okay, let's take a look at our last example. So we have natural log of x over x. And again, it's very, very helpful. We've talked about this before, but for you to understand the graph of natural log of x, it goes through the point 1, 0, looks like this. So if I just plug in the limit as x goes, oh, I don't want that there. The limit as x goes to infinity of natural log of x over x, eventually natural log will reach infinity. It just takes forever. It grows very, very slowly. But eventually it'll get there. So that's infinity over, and then the x, infinity. So by L'Hopital's rule, that is a case where I could apply L'Hopital's rule. The limit as x goes to infinity of natural log of x over x is equal to the limit as x goes to infinity of 1 over x, because I differentiate the top. Derivative of natural log of x is 1 over x. Over, and then I differentiate the bottom. Derivative of x is just 1. So this is now 1 over infinity, which is 0. And again, I only needed L'Hopital's rule one time. But before I started, I had to make sure that I had verified that it was infinity over infinity form or 0 over 0 form. If it works for you, if it applies to your situation, L'Hopital's rule is a really fast way to find limits. It's a fast way to find limits that you might have been able to find in earlier chapters. This just works better if it applies. So again, make sure that you can justify that you're in a 0 over 0 case or an infinity over infinity case. And as long as that's true, L'Hopital's rule tells you that you can differentiate the top and differentiate the bottom, and that those two limits would be equivalent. That's it for L'Hopital's rule.